After going over what sparse autoencoders are and why they matter, this last video, led by Alexander Rocha, founding engineer at ZeroEntropy, explores some of the empirical discoveries and use cases for SAEs.
What does this actually look like, and what interesting applications are there from research right now that sprung out of this research? One that's very close to my heart, and one that Anthropic focuses on quite a lot in their research, this is from one of their blog posts actually, is proving that LLMs have the capacity for forward planning. In other words, that they are not just next token predictors, and that they are able to, at the end of one line of a poem, already be thinking of the words that they want to end the next line on so as to make a rhyme. So, we tell it, make a rhyming couplet. Oops. That is a pair of lines that rhyme. He saw a carrot and had to grab it. Now, what rhymes with grab it? Well, among other things, the word rabbit. And what this diagram is showing here is that in the deconstructed SAE dictionary of the model activations, at this point in time, at the end of the first line, he saw a carrot and had to grab it. The feature in the SAE dictionary associated with rabbits was already firing very strongly. And the only reason why that would ever happen is because the model is thinking that it should probably target that in the future. And so when it goes through the process of next token prediction, it outputs the new line, his hunger was like a starving, it ends up saying the word rabbit, almost always. This is quite interesting, because this puts to rest a discussion that had been going around in the space for quite some time of like, are LLMs just strictly next token predictors? Are they just stochastic parrots and incapable of forward planning? Evidently, they are. And what's interesting is that in the circuit tracing, what they found was that actually first, the feature associated with any token, any word that just ends in this eat rhyme sound was activated first. And then later we ended up with rabbit, habit, and so on. So it actually deconstructs specifically neurons associated with rhyme planning. And not just with rhyme planning in general, but rhyme planning for individual sounds. We see something very similar when we try and trace the graph of translation. Le contraire de petite est, that is the opposite of small, petite, is, and then what is the next token it's supposed to output? Well, these three input tokens give you opposite in French. And then if you map how the LLM is thinking, what SAE dictionary features are activated as you go through the next token prediction. It activates this X as opposite of X feature. It activates a multilingual feature. And then it goes through another feature that just gives you the opposite. And you end up with large, and then saying large in French. And then you end up, of course, with the correct token, the next word, which is grand, large. That has all been on the interpretability side of things. But what about the aforementioned use case of steerability? Well, if you artificially clamp the value of a neuron associated with specific female names, Margaret, Sarah, Ruth, up or down, then you can get it to give outputs that it would not otherwise give. So here's the prompt. I always loved visiting Aunt Sally. Whenever I was feeling sad, Aunt, you would expect that, given no other context, it would almost always respond with Sally, right? And if you look at the far right of this graph, where on the x-axis you see 1x, that is like no intervention, that's basically always the case. Like the probability of outputting Sally is basically 1. But if you clamp the neuron in the SAE dictionary that is associated with the word Sally or the name Sally down so that the model just can't output that, then you see the probability slowly go down, and then Margaret, Sarah, and Ruth, other potential, female names that roughly belong to the same generation, start to increase. So not only does the model like figure out that, oh, I need to output a different name, it outputs names which could conceivably be that of another aunt of equal age. One of the very coolest things that has been found in this research is that for the first time, we found that LLMs have the capacity for introspection. And what we mean by that is that without giving a token output, the model is able to describe a change in its internal state. So what was done here was that first we trained an SAE, I think this was on Claude Haiku 3.5, or maybe Claude Sonnet 3.5. And we figured out which of the SAE dictionary features, which of the neurons in the SAE hidden layer, was associated with all caps, just outputting in all caps. And in fact, I'm sorry, I misspoke there. That wasn't even a directly learned activation. All we did was simply put these two texts through the model and then correspondingly through the SAE and subtracted the two. The only difference, of course, being that one of them has "Hi, how are you?" in all caps and the other one doesn't. You subtract the two, and then you get a corresponding all caps vector. Interestingly, you can do this directly in the activation space of the LLM. You can also do this in the SAE dictionary space, and that tends to work a little better. There's been some recent research on that. In any case, you extract some all caps vector, and as you're just telling the model to go through this prompt, you put that in there. You like add that delta into each one, into whatever layer for every single token that it's outputting. And you basically ask it, there's a 50-50 chance that I'm going to be injecting thoughts into your mind, Claude. I want to assess how well you can detect when I inject thoughts. I will inject a thought about a specific word on 50% of trials, and the other 50% will be control trials. I won't do anything. Claude responds, okay. We do this, we inject the all caps vector, and we ask it, what do you feel? Do you detect an injected thought? And it responds, I notice what appears to be an injected thought related to the word loud or shouting. It seems like an overly intense, high-volume concept that stands out unnaturally against the normal flow of processing. Now, keep in mind that there's nothing in the prompt, there's nothing in the tokens to indicate to the model that this would be the case. And importantly, the tokens that the model outputs with do not exhibit the behavior up until the word which determines the answer, loud in all capitals. So it can't be the model's output that it's, in a feedback loop detecting this from. The only way it could give this, and it gives this with, statistically significant, vastly statistically significant frequency, is if it just has some internal mechanism to detect how it's feeling, thinking, for lack of a better word. This is quite interesting. And they reran this experiment with many different vectors. It didn't work for all of them. But curiously, it worked for the one associated with dogs. They just clamped that one very high, and the model just responded with, I feel something fluffy in my mind, something soft and fluffy. You can read the blog post, which I'll link to later in the comments, but it's very fascinating.